Welcome back to the video course on fluid mechanics. So, in the last lecture we were discussing about the fluid statics. So, we have seen the various methodologies for pressure measurements, and then we have seen the manometers, then automatic measurement equipments like Bowden gauge, and then we were discussing about the forces on submerged surfaces in static fluid. So, as we discussed in the last lecture, the important features of static fluids are the hydrostatic vertical pressure distribution is always assumed generally, and second one is pressure at any equal depths in a continuous fluid are equal, and then as we have already seen the Pascal law, that means that pressure at a point acts equally in all directions. That is very much valid in all the problems which we are discussing, and then the forces from a fluid on a boundary acts at right angles to that boundary, as we have seen earlier. So, now based upon this we have already seen for say the forces on a submerged surface in static fluid, and then we have seen the resultant force is equal to P1 into delta A1 and delta plus P2 into delta A2 as shown in this figure. This we have already discussed in the last lecture, and also we have seen the forces on submerged surfaces in static fluid, and the resultant force is equal to pressure into area of plane, that is equal to P into A as shown in this slide. So, now in today's lecture we will discuss the resultant force and center of pressure on submerged inclined plane surface. So, as I mentioned in the last lecture, so when we have got a tank and then we are putting a small inclined plane like this, we want to find out the resultant force on this plane, and then what will be the center of pressure on this inclined plane. So, that is what we will be discussing today first. So, here in this slide you can see that say here there is the fluid, there is a fluid in a tank like this, and then its free surface is atmosphere pressure distribution here you can see, and then there is an inclined plane like this, and then say the fluid density is rho, and say we are considering now an elemental area delta A like this, and then the total area of the inclined plane is A, and we want to find out the resultant force and the center of pressure. So, here this element which we are considering, to that the depth is Z as you can see here in this slide, and then the total area is concerned to the center of pressure from the top it is Z bar, and resultant force is R. So, in the next slide and we will see how we can determine this resultant force, and this plane is this inclined plane surface is say inclined at angle theta as shown in this slide. So, now the resultant force and center of pressure. So, the pressure on element delta A, as we have seen in the previous slide, is P is equal to rho into G into Z, where rho is the density of fluid, G is the acceleration due to gravity, and Z is the depth at which the element delta A is concerned. So, force on element A is equal to P into delta A, that is equal to rho into G into Z into delta A, and then finally we can say take the sum of all the different elements which we are considering the plane area, and then the resultant will be R is equal to rho into G sigma Z into Z delta A. So, that is the resultant force is equal to rho into G sigma Z into delta A. So, this Z into delta A, sigma Z into delta A can be represented as A Z bar. So, in the inclined plane that is equal to A x bar sin theta. So, that is equal to first moment of area. So, the resultant force on plane R is equal to rho G A into Z bar. So, if you substitute this sigma Z into delta A in this expression, so that you will get the resultant force on plane R is equal to rho into G into A Z bar, or this Z bar can be written as x bar sin theta. So, that is equal to rho into G into A x bar sin theta as shown in the last slide. So, here you can see which is already explained what is the Z bar, and here this is Z, this is theta, and x bar sin theta is this with respect to the distance measured here. So, now we got the resultant force. Now, the center of pressure is the point through the resultant point through which the resultant force acts. So, here you can see say the point where the resultant force acts, that is called the center of pressure. So how to find this center of pressure? So with respect to this problem which we are discussing now, we can take the moment of R, the resultant force about the point O. So that will be equal to sum of moments of forces on all elements of delta A about A. So that is equal to, so that we are finding out the center of pressure by taking moment of the resultant force about O, that is equating that to the sum of moments of forces on all elements of delta A about A. So force on delta A is equal to, as we have already seen, rho g z into delta A, that is equal to rho g into s into sin theta delta A with respect to the previous slide. So moment of elemental forces about O is equal to rho into g into sin theta delta A into s square. So and then sum of moments of forces on all elements of delta A about O is equal to rho into g into sin theta into sigma s square delta A, and then finally the moment of R, the resultant force about O, is equal to rho g into ax bar sin theta into sc. So now we will equate this moment of R about O to the sum of moments of forces or all elements of delta A about O. So that we are equating rho g into ax bar sin theta into sc. This is equal to rho g sin theta into sigma x square delta A. So finally we get the center of pressure from O is equal to sc is equal to sigma s square delta A by ax bar. So here in the previous slide with respect to this figure we have already seen. So we want to find this center of pressure with respect to the resultant force and then with respect to the elemental area which we are considering. So finally we got the center of pressure from O as is equal to sigma x square into delta A by ax bar. So this in the previous slide, as we have seen here, this center of pressure is equal to sigma x square delta A by ax bar, and then the second moment of area about this point O which we are considering can be written as, that is equal to sigma s square delta A. So finally this sc can be written as a ratio of second moment of area about a line through O to the first moment of area about a line through O. So sc is equal to second moment of area about a line through O divided by first moment of area about a line through O. So that gives the second this sc. So that is what we have already seen, this center of pressure is sc. So that is what we are getting here. And then depth of center of pressure d is equal to sc sin theta, since we are considering an inclined plane as in the previous slide. And then how to find out this second moment of area about a parallel axis, say the axis like in this figure in this slide here. So if you want to find the second moment of area about the we can use the parallel axis theorem. So with respect to that we can write IO is equal to IGG, this axis, plus AX bar square. So for this rectangular element like this, it will be BDQ by 12. So this way we can find the second moment of area from parallel axis theorem, and then the center of pressure will be the ratio of second moment of area about a line through O to the first moment of area about a line through O. So like this we can determine the resultant force on the inclined plane, and then we can determine the center of pressure where the resultant pressure is acting on the inclined plane. So now we will discuss a vertical surface instead of inclined plane. If you consider the vertical surface, as you can see here in this slide, for the case of vertical surface, this is a tank where we want to find what will be the resultant force acting on this particular wall here. So here you can see this height, the height of the liquid or the water here is h, and here the surface of the tank is affected by the atmospheric pressure. So with respect to this, we can write the resultant force is equal to half gamma h into b into h. So where b is the width of the tank which we are considering, so that we can write this as the resultant force is equal to the volume which we are considering on this particular with respect to this elemental volume. So that can be written as gamma h by 2 into the cross sectional area b into h. So the resultant force is equal to this the area of this triangle. So that we can write that is equal to half into h by 2 into a. So that is the resultant force acting on this vertical surface with respect to this tank. So the area of triangle is equal to resultant force per unit width, and in this case the center of pressure is equal to 2h by 3. So this way we can determine the resultant force on either inclined plane, or we can determine the resultant force on a vertical surface, and we have already seen the resultant force with respect to other surfaces, and then next we will be discussing about the resultant force and the center of pressure with respect to curved surface. So before that we will discuss a small example problem. So the problem here we are discussing is, say there is a rock-filled dam like this. So we want to determine what is the simplest resultant force from water and where does it act on 120 meter high and 1200 meter long straight rock-filled dam. So that is the problem. So here you can see the dam is, say the base width is 285 meter and the height is 120 meter and top width is 10 meter. So and here this is an inclined plane here on AB where the water surface is acting. So here this is the water surface is acting here. So this is water in the reservoir. So we want to determine the simplest resultant force and then where it is acting. So this is an inclined plane. So we can determine this inclined plane AB, that distance can be determined. So that will be AB will be equal to 120 square this height square plus 75 square this base width. So that will give AB, and then we can draw the pressure distribution triangle like this. So on this AB the resultant force will be acting like this R, and then say the base on the base the pressure will be gamma into H. So gamma, if you take 10 kilonewton per meter cube, so that will be 10 into 120 kilonewton per meter square at the base, and then the resultant force will be R is equal to half into this base gamma into H into this length AB, this height AB which we are considering in this inclined height. So that will be 141.5 which we have already determined, multiplied by the width of the length of the dam, that is 1200 meters. So the resultant force will be equal to half into R into 10 is the gamma, 10 kilonewton per meter cube, 10 into 120 into 141.5 multiplied by 1200. So that will be equal to 101.88 into 10 to the power 6 kilonewton. So the resultant force is acting this R at this particular location. That will be the location will be x bar will be equal to AB by 3 from the base. So that will be 141.5 by 3 from the base. So this is the center of pressure, and the simplest resultant force will be this much R, and it will be acting at this location. So this is a simple problem. Say here with respect to a rock-filled dam, we have calculated the simplest resultant force and then the location of the center of pressure where the resultant force is acting. So now next we will discuss the force on submerged curved surface. So we have seen the force acting on a horizontal plane, we have seen the force acting on a vertical plane, also we have seen the force acting on an inclined plane. So when say as far as fluid statics is concerned, when the force is acting on a curved or curved surface, then we have to say, for example, if you consider this bottle here, so this side of the bottle is curved. So you can see that when we have to determine the force on a curved surface like this, we have to take the horizontal component and vertical component, and then we have to determine the resultant force acting with respect to the curved surface. So now we will discuss the force on a submerged curved surface. So here in this slide here you can see here the fluid is at this location. Here there is a small tank, and then there is a curved gate like this. This is a gate here, the curved light gate in the location say here AB, and then the fluid is above that gate. So, we want to determine the resultant force acting on the gate with respect to this fluid above the gate, and then we want to find its location or where the force is acting, the resultant force is acting. So, here the surface is curved. So, forces on each element of surface are not parallel, as we have seen in the case of vertical surface or horizontal surface, it is not parallel. So, we have to take it the horizontal component and the vertical component. So, first we will be calculating the horizontal and the vertical components, and finally we will obtain the resultant, and then we will obtain its direction. So, here with respect to this gate, curved gate, here you can see this RH is the resultant force acting on this gate, and then with respect to the fluid weight there will be a vertical force or RV acting in this direction, and then we have to find out the resultant of this RH and RV. So, that will be acting in this direction R. So, we want to find out this R with respect to the curved surface. So, for this purpose, say here the resultant force, the resultant horizontal force of fluid above the curved surface is resultant force on projection of the curved surface. So, we can project this curved surface say to a vertical plane like this, and then we can find out what will be the force acting on this vertical surface. So, that will give the resultant horizontal force. So, in the case of this curved gate here, so the horizontal force we can determine by projecting the curved surface on a vertical plane. So, in this case this is the vertical plane where we are projecting this curved surface, and that will be the resultant horizontal force, and then it will be acting through the center of pressure projection of the curved surface on vertical plane. So, here this will be the center of center of pressure where it will be acting. So, the horizontal force, the resultant horizontal force is acting in this direction, and then with respect to this horizontal, the vertical projection, here it will be the center of pressure. So, similarly the case of the vertical component, so the resultant vertical force will be, say, as far as this gate is concerned, the resultant vertical force will be the weight of fluid above the curved surface. So, here we have the curved surface. So, what will be the weight of fluid above this curved surface, that we can determine, and then that acts through the center of gravity of the mass of fluid. So, here as far as this mass of fluid were just above the curved surface. So, this much fluid where say we can determine the weight of the fluid above this curved surface, and then what is the position of the center of gravity we can determine, and then the resultant vertical force will be this weight of the fluid above the curved surface, and then it acts through the center of gravity of the mass of fluid. So, we are finding out the horizontal resultant horizontal force, and then where it is acting, and then we are finding out the resultant vertical force, and then it acts through the center of gravity of the mass of fluid above the gate which we are considering. So, like this we are splitting the resultant force to resultant horizontal force and resultant vertical force, and then say for example, if you consider in this particular case the resultant force, say if you want to find out, see the case of vertical force, here the liquid is there and here it is empty. So, if you want the effective vertical force, it will be V1 here, and then V2 here, and V1 just above that will be the effective vertical force. And in the case of, say, if the liquid is kept here in the bottom as in the second figure here. So, here V1 is effectively, this is the fluid here, and the total fluid will be this V1 plus V effective just above the gate. So, the total will be V1 plus V effective, but V effective we can find out Vt minus V1 from this line, from this figure. So, the resultant force finally, after determining the horizontal force and the resultant horizontal force and the resultant vertical force, the resultant force we can determine R is equal to square root of RH square, the whole square of resultant horizontal force plus the square of resultant vertical force. So, its square root gives the total resultant force as far as the curved surface or the submerged curved surface is concerned, and then the angle of resultant force we can determine theta is equal to tan inverse RV, the resultant force in the vertical direction divided by the resultant force in the horizontal direction. So, theta is equal to tan inverse RV divided by RH. So that gives the angle. So here you can see this is the RH and this is the RV. So the resultant force will be square root of RH square plus RV square, and then this theta, tan theta will be equal to the tan will be equal to R, say this RV divided by RH, and then finally we can get theta is equal to tan inverse RV by RH. So like this we can determine the resultant force, and then the where it is acting, the location of the where the resultant force is acting, that we can determine through this by taking the horizontal component and taking the vertical component as explained here. So now as we have discussed, the say the fluid, say a gate is in this fashion and then the fluid is just above the gate. So the fluid is above the surface, so we can see that the effective pressure is acting like this in this slide. So the pressure is acting just normal to the curved surface in this direction, and the effective force we can determine as we have already resultant force we can determine as we have seen the previous slide. And in this case, the second case here in this figure, you can see the fluid is just below the gate. So the resultant force is acting, say with respect to this, the pressure is acting in this direction. So P is acting, no fluid actually above the surface, and the effective, the vertical force we have seen how we are calculating the previous slide. So like this we can determine the effective vertical force, resultant force, and then horizontal force. And finally here we will summarize how we are doing as far as the curved submerged curved surface is concerned. So first we can identify the effective column fluid necessary to cause the fluid pressure on the surface. So here you can see in this figure the effective fluid pressure we can calculate, and then second one is determine the volume of the effective column fluid, and then calculate the weight of the effective column of fluid which is obtained as rho g into V effective. Then we can find the location of Fe through the centroid of V effective, and then we have already seen this is as far as the vertical resultant force for the various cases are concerned, and then horizontal force will be just acting through the center point of the projected area, and that also we can determine as we have seen in the previous case. So like this we can determine the resultant force, and then where the resultant force is acting as far as submerged curved surface is concerned. So now we have already seen, say, how we are determining the resultant force, and then where the resultant force is acting as far as the curved surface, then inclined plane, vertical plane, and horizontal plane. So now we will discuss some of the applications of this, some practical applications. So how we can determine the resultant force, and then how we can determine the center of pressure for some practical cases. So first we will consider a water tank. So here you can see in this figure, in this slide here you can see a water tank. So if you want to find out the pressure at sidewall, we have already discussed it earlier. So P is equal to gamma into B into H by 2. So this the area of this triangle here, that gives the pressure at sidewall. So this gamma H is the pressure at the bottom, and then H is the water column height. So this is the resultant force P, and it acts at H by 3, this 1/3 of this height from the bottom. So this is as far as how we can determine the resultant force and center of pressure for water tanks. So this is the first case, and then second case, if you want to determine the resultant force and center of pressure or application in the case of a sluice gate. So sluice gates are very much used in the case of many of the hydraulic structures as far as canals or dams are concerned. So how we can determine the resultant force? So here this slide shows, so here there is a sluice gate, and here the water column on the upstream side is H1, and the downstream water column height is, the depth of water is H2. So we can determine if you want to find out the pressure acting on this gate, so we can determine P1 is equal to, P1 is acting, what is acting on this gate here, this is the gate location, P1 is equal to gamma A into H1 minus H by 2. So where H is the height of the gate. So P1 what is acting on this gate is equal to, only effectively acting on the gate is equal to gamma A into H1 minus H by 2, and the force acting from the downstream side, P2 is obtained as gamma A into H2 minus H by 2. So, the effective pressure or the effective force acting on this the gate is equal to P is equal to P1 minus P2. So, this is the case of a sluice gate, and the next case is say if you want to determine the resultant force and center of pressure as far as a dam is concerned. So, this we have already discussed earlier as in the case of a problem. So, here you can see if it is a concrete dam here. So, if you want to find out the certain force and center of pressure, so here this the gamma H below on the surface gives the pressure here, and then total pressure is the area of this triangle. So, that is equal to say gamma Ax bar, or in this case we can see the gamma H into H by 2 is the per unit width, and you can multiply by the width of the where this dam is, that river width, or where that section is there. So, that will give the total pressure, and here the pressure will be acting at H by 3, very similar to the case of a tank which we have discussed. So, this gives the pressure on a dam. So, like this we can see so many practical applications, say in the case of many of the cases like reservoirs or dam with respect to dams or water tanks. In many cases we have to determine the resultant force, and then we have to determine the center of pressure, so that we can properly design the hydraulic structures, or we can see how much pressure is acting, and then properly say manage or design the section. So, like this various other applications also we can find. So, as we have seen here, the pressure acting from the top is equal to x bar plus Ig by Ax bar, as we have already seen in the previous case, and then finally the resultant force is equal to P is equal to gamma Ax bar in the case of a dam. So, here it is P is equal to gamma x square by 2 for a unit width. So, that is and then it is acting at 2h by 3 from the top and h by 3 from the bottom. So, this also we have seen. So, now with respect to this resultant force and center of pressure applications, we will discuss a few example problems. So, first example is we will discuss a problem where we want to find out the say there is a sluice gate, like in this here you can see this figure shows a sluice gate, and then there is a on the upstream the water. We want to find out this depth of water with respect to say for which the valve will open. So, there is a valve here which is hinged at this point, and below the downstream side of the sluice gate the water depth is 225 millimeter, and the gate is pivoted at a height of h is equal to 100 millimeter, like this. So, the problem statement here is, so we want to determine there is an automatic valve, which consists of a 225 into 225 millimeter square plate of uniform thickness weighing 200 Newton as shown in this figure. The valve is pivoted about a horizontal axis through A, this is A, located at a distance h is equal to 100 millimeter above the lower edge. Determine the depth of water D, this depth of water D for which the valve will open. So, here the problem statement is, here we have got a sluice gate, we want to find out this depth D for which the valve will open. So, or the minimum depth for which the valve will open. So, here already there is water depth 225 millimeter in the downstream, and here the valve is pivoted at h is equal to 100 millimeter from the bottom. So, we want to find this depth D for which the valve will, the minimum depth for which the valve will open. So, for this problem now we will consider three cases. So, first case is, say we can see here, for opening of gate the resultant should be at A. So, if you consider the various forces acting and then if you are determining the resultant force. So, for to open the minimum, if we want to find out the minimum depth of water, in this case we want to find that the resultant should be the resultant of this water column on the upstream side of this sluice gate, that should pass through this hinge at A. So, that will be the limiting value. So, to solve this problem, here we will consider three cases. So, first case is say when say if D, the depth of water column on the upstream side, if D is less than 225 millimeter. Here the downstream water column is 225 millimeter. So, if it is the upstream depth is less than 225 millimeter, then what happens? So, we have already seen the center of pressure will be H D by 3. So, D, when D is less than 225 millimeter, then it will be less than say 100 millimeter, or this will be less than 75 as far as where the center of pressure is acting. So, you can see when I draw the center of the resultant force or pressure distribution diagram here, you can see this resultant force will be less than this 100 millimeter, which is the height of the wall hinge which we are considering. So, when it is less than 100, then you can see that it will not open. So, first case when D is this depth of the water column on the upstream is less than the downstream depth of 225 millimeter, gate will not open. Then the second case we will consider when the upstream depth is equal to the downstream depth. So, D is equal to 225 millimeter. So, in this case here you can see D is equal to 225 millimeter, then the you can see that the pressure distribution with respect to the gate here is 225 millimeter, pressure distribution will be like this, and then we know that the center of pressure will be, this is a vertical surface. So, the center of pressure will be D by 3 from the bottom. So, here with respect to this, say it will be 225 for the limiting case, 225, it will be 225 by 3 from the bottom surface, it will be 75 millimeter. So, this 75 millimeter is again less than this depth H where the A is located, where the pivot is located. So, since this D by 3 is 75 millimeter less than 100 millimeter, in this case also gate will not open. So, the third case what we will be considering is when D, the depth of upstream water level is greater than 225 millimeter. So, in this case the pressure distribution can be drawn like this, say here with respect to the gate, this downstream depth this is up to 225 millimeter, and then above that also the with respect to the water, there will be the pressure distribution will be extended like this. And then if we consider this particular location, then you can see where the downstream height is coinciding with the upstream height. This location if you consider, you can see here, say with respect to this, you can see here, this is the particular location where the gate is located. So, for that we can draw the pressure distribution. So, this will be a trapezoid pressure distribution like this, and here it will be rho g into d into b. So, this we can split into one rectangle type pressure distribution and one triangle type pressure distribution. So, this will be the rectangle type, and so this we can split into one triangle distribution and one rectangle distribution. So, finally we will get this will be equal to F1 plus F2, for F1 stands for the rectangle pressure distribution with respect to this, and this F2 is with respect to this triangle pressure distribution. So, from this we can write we can solve this problem by equating F1 is equal to, we can calculate the pressure the force F1. So, that is F1 is equal to rho into G into D minus 225 into B into 225 Newton, acting as 225 by 2 from the bottom. So, that is correspond to this force distribution F1, and then we can determine F2 for this triangular pressure distribution is concerned. F2 is equal to half into rho into G into 225 into B multiplied by 225, that will be acting this 225 by 3 from bottom. So, here we are assuming D is the limiting case of 225. So, if it is limiting case up to this 225 by 3, since we are considering only up to this. So, this is F1 is calculated, F2 is calculated, and now the resultant force you can see this F1 plus F2. So, Fr is equal to F1 plus F2, and then we will take a moment Fr into x bar. So, here this total, as far as the total force is concerned, Fr will take a moment Fr into x bar, and that will be with respect to this F1 into 225 by 2 plus F2 into 225 by 3. So, this is from the bottom. So, for opening gate we know that the with respect to this should be either 100 millimeter or just more than 100 millimeter. So, if we put this x bar is equal to the minimum of 100 millimeter, then we will get x bar is equal to if you substitute for x bar is equal to 100 millimeter x minimum, then we will get finally we can equate this Fr is equal to F1 plus Fr x bar is equal Fr into x bar is equal to F1 into 225 by 2 plus F2 into 225 by 3. Finally, we will equate all this. Finally, we will see that the D minimum, that means here the minimum depth of water to open this gate, the sluice gate, will be 450 millimeters. So, in that case the gate will be opening. So, finally, we can determine the depth of water D for which the valve will open will be 450 millimeter. So, this way we can solve this problem where we discuss the pressure distribution and the force as far as the sluice gate which we considered here F1 and F2, and then we have determined the with respect to after taking a moment say with respect to this pivot, we want to see the depth, minimum depth at which it will start to open. So, that we have calculated as D minimum is equal to 450 millimeter. Okay, next problem which we will be considering is we will consider an arch dam, and we want to determine the simplest resultant of the hydrostatic force. So, here in this figure, so we want to determine there is an arch dam here, and here there is a reservoir, and the radius of this arch dam is 60 meter, and we want to determine with respect to this reservoir, we want to the height of water level is 40 meter. We want to find the simplest resultant of the hydrostatic pressure on the arch dam. So, this is, here is the dam, and here is the reservoir, and the depth of water is 40 meter. So, here with respect to this figure, first we will find what will be the pressure distribution at the bottom of the dam. So, here if you consider like this in this here 40 meter, so it will be rho g into z at the bottom. So, this figure here you can see that from due to the effect of the reservoir, the force will be acting normal to the surface, and then what we can do is in a simple way we can just take what will be this inclined plane. So, we can just make this an approximation. So, we can just find what will be the length of this inclined plane. So, here this is 60 meter radius. So, we can find that this will be 60 root 2. So, finally, we can determine the resultant force as, so this with respect to this half gamma into this 40 is the height, and then we multiplied by again 40 into 60 root 2, which is the on which this area is acting. So, the total the simplest resultant in this case for this arch dam will be half gamma 40 into 40 into 60 root 2, where gamma is the specific weight of water, and this will be acting at 40 by 3 from the bottom. So, this is the case of a how to find out the simplest resultant for of the hydrostatic pressure on an arch dam. So, now one more problem we will consider. So, here the last problem here, there is a the problem statement is the quarter circular uniform gate, there is a gate AB has a width of 6 meter, and the gate controls the flow of water over the edge B. The gate has total weight of 6,800 kilogram and is hinged about its upper edge A. Find P, the force required to keep the gate closed. So, here we have got a gate, and then on this side we have water, and then the gate radius is 9 meter, and it has got a width of 6 meter. So, we want to find what is the force P which should apply from this other side, so that the gate will be kept as closed. So, gate, if you want to keep the gate as closed, what should be the pressure P which should be applied from this side. So, that is the problem. So, the gate, the total weight of the gate is 6,800 kilogram. So, here we can consider the free body diagram or all the pressure and forces acting as far as the problem is concerned. So, here P is the force which we want to determine, and here with respect to the water column there will be a force acting like this, and then the weight of the gate 6,800 kilogram also we have to consider. And if you consider this as y axis and then x axis, and now to solve this problem we can take the moment of water pressure about this location A. So, that we can determine by taking an integral 0 to pi by 2, since this angle is 90 degrees. So, we can find the moment of water pressure about A by taking integral 0 to pi by 2 gamma, the specific weight, multiplied by the radius of the gate 9 into 1 minus cos theta. We are considering this as angle theta. So, this will be into 1 minus cos theta. So, that will be the pressure intensity acting upon this gate multiplied by the area delta A, since we are integrating. So, delta A will be 6 into 9 into d theta. So, this we are taking a small angle d theta here, and then we are finding the area as 6 into 9 into d theta, and then that will be multiplied by the perpendicular distance to this area and 9 sin theta. So, this will be 9 sin theta. So, that is equal to, if we integrate, it will be, and applying the taking the multiplying the 6 into 9 and all this value to be 4,374 gamma. Gamma is specific weight of the water. So, 4,374 gamma integral 0 to pi by 2 sin theta minus sin theta cos theta d theta. So, this is with respect to this integral, and then after the integration and applying the limits from 0 to pi by 2, we will get this as 2187 gamma, and if we take gamma as 9,818 Newton per meter cube, finally we will get the moment of water pressure about A. And then finally, to find this P, we will be taking a moment of all the forces. So, this integral we have considered only as far as this water acting on this the gate is concerned. So, if you want to find the pressure P, now we will be considering all the forces as far as the this gate is concerned. The forces here are the water pressure acting from this side, and the force which we want to keep it closed, this P, and then the weight of the gate is 6,800 kilogram. So, if we want to find P required to keep the gate closed, finally we will be taking a moment of all the forces about this location, this point A. So, that P is concerned, P into 9. So, P into 9 is equal to, we have already determined what will be the moment of water pressure about A. So, that minus the gate is concerned, there will be another force will be acting. So, its moment 6,800 into 9.81 into 2. So, it will be acting, this weight of the gate will be acting 2r by pi from this side. So, it is 2 into 9 by pi. So, from this equation, if we take the moment of all forces about this location A, we can finally determine P. So, in this case we can determine P as 2343.31 kilonewton. So, like this we can consider all the forces acting on the gate, the water pressure from this side, and the force which we have to keep the gate closed, that P, and then the weight of the gate. So, like this we can solve various problems to find the resultant force, center of pressure, and its various applications, as we have demonstrated in all these examples discussed here. So, now the next topic we will discuss the buoyant force. So, the buoyant force we can define as, it is the resultant fluid force acting on a body that is completely submerged or floating in a fluid is called the buoyant force. So, now if we consider some water here in a container. So if you want to find, say, what is buoyant force. So now if you just put, say, like this, if you want to submerge, if you floating body like this, we are now just partially submerged here on in this water. So you can see here, say, it is the buoyant force is the resultant fluid force acting on the body that is partially submerged or floating. So here this body is floating here. So you can see that there is some force is acting on its surface, that is why it is floating. So either it can be submerged or it can be floating. So this force is called the buoyant force. So the buoyant force will be generally equal to the specific weight of the fluid multiplied the volume of the body, whether it is partially submerged or fully submerged. So based upon this buoyant force, Archimedes formulated this principle called Archimedes principle. So this is defined as the when a body is immersed in a fluid or wholly fluid, either wholly or partially, it is buoyed or lifted up by a force which is equal to the weight of the fluid displaced by the body. So this is called the Archimedes principle. So here you can see in this case, what is this floating body, how much the partially submerged body, how much is the fluid which is displaced with respect to its weight. So that should be equal to the what is acting upon on the body. So that is the Archimedes principle. So with respect to this, say here you can see in this slide, say if you consider the Archimedes principle. So here there is a buoy on the in a fluid. So the hatched volume we can calculate. So this the buoyant force will be the WT where FB is acting. So WT is the of liquid displaced. So with respect to this buoy, some liquid will be displaced. So that we can calculate the weight of the liquid. That means WT is the weight of the liquid displaced. So that is gives the buoyant force. So and then we can determine the centroid of the displaced liquid, so that we can see where it is acting. So like this buoyant force is very important in as far as, especially as far as the static fluid is concerned, as we have discussed here. And buoyant forces passes through the centroid of displaced volume, as we have already discussed, and the center of buoyancy is defined as the point through which the buoyant force act. So this buoyant force is passing through the centroid of displaced volume, so from which we can determine the center of buoyancy. So here this you can see, this is the body where it is say already wholly submerged. So with respect to that, how much liquid is displaced, and then with respect to that we can determine the buoyant force, and then we can determine the center of buoyancy. So here you can see this buoyancy force is equal to F2 minus F1. So F2 is the force acting upon the body which is submerged fully or submerged partially. So that is the F2, and then the with respect to this F1 is the force which is acting with the weight of the fluid which is acting upon this. So FB, the buoyant force, is equal to F2 minus F1 and minus W, where W is the weight of the body, and F2 minus F1 is equal to gamma into S2 minus H1 into A, and finally the buoyant force is equal to gamma into the volume of the fluid which was displaced. So this is the way which we determine the buoyant force, and then we can determine this principle for many other applications. Like if you want to determine the specific gravity of liquid, we can use a hydrometer. So a hydrometer is a equipment which you will be putting which is just like a cylindrical form, an equipment where some fluid is filled, and then it will be putting into the liquid, and then this principle of buoyant force is used to determine the specific gravity of liquid. So the Archimedes principle and the buoyant force and center of buoyancy is very important in many of the fluid flow problems. So we will be discussing further say the with respect to this buoyant force and center of gravity, how we can determine, for say, whether a body, whether a submerged body or a floating body is stable or unstable, that we will be discussing in the next lecture. So buoyant force, with respect to buoyant force, we can determine the center of buoyancy, we can determine, then we can find out the center of gravity, and then we can see whether the body is, the floating body is say stable or unstable or in equilibrium condition. So that we will be discussing in the next lecture.